Hey kids, time to start chapter 4, higher order linear differential equations. Should have put differential in there, huh? So picture of some pretty cool stuff here. Now this is a second order, but still higher order, right? So we're going to generalize all the stuff that we have done so far has been with linear or second order. Our job now is to generalize for higher than second order. We're going to start though reviewing, right? So here, the next couple slides just has a whole bunch of words, bleh, right? Just a whole bunch of words on it. They're all words you know. I'm just going to generalize to higher order, right? So a linear, right? Because I just have a y to the first here. Ordinary differential equation of order n, right? So first order, second order, third order can be expressed in this form, right? We assume that we often call these, right, like P of X and Q of X, right? Blah, 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 blah. We sometimes call them that. If they're constants, we just call them A, B, and C, and so on. Notice that this is a non-homogeneous differential equation. We assume that all these functions are continuous and real valued, right? We're not dealing with imaginaries. That's later. We do all these things are true on some interval. We say that this leading coefficient is not 0 on any place on the interval, so that, because remember, a lot of times we end up in a lot of math we want to get the coefficient of the highest order to be 1. So we divide everybody by this number or this function. And of course, we can't do that if that's 0, but if it was 0, then this order wouldn't be there. So it's kind of a silly statement. Another theorem, right? If the functions blah, blah, blah are continuous on that open interval, then there is exactly one solution of the differential equations that satisfies any given initial conditions, right? We don't always have initial conditions, right? Sometimes we just find the general solution, and that solution exists throughout the given interval. Oh, who's that? Oh, it's wonky Wronskian. Remember, here I'm just going to take wonky and make him bigger. He's even wonkier. If I have a fundamental set of solutions, not just 2, right? But let's say I have as many as I want solutions of a differential equation that would be then the nth order, right? And if I calculate the Wronskian, which is just a determinant, and the Wronskian is not equal to 0 for at least one point in my given interval, then every solution can be expressed as a linear combination of these. This is old news. It's just that we only dealt with y1 and y2. And so when we did the determinant, which was our Wronskian, we just used y1 and y2, and then y prime of 1 and y prime of 2, right? Well, what if I don't have just 2? Can you find the Wronskian of this fundamental set of solutions? So it's a 3x3 matrix, which I'm going to turn into determinants, so I need to have those. Do you remember how to do the determinant of a 3x3 matrix? Now, if this was numbers, I could put this into my calculator, but it's not numbers. So I do have to remember, but we did this in multivariable, right? So I sometimes teach when I do matrices in Algebra 2, I sometimes teach this augmented matrix way of finding it, but we usually, especially since we dealt with I, J, and K, remember that? So we're just going to use the minor determinants. So we're going to say x squared times the determinant of those values, but what's that going to be? 36 minus 36x to the fourth minus 24x to the fourth, right? Then we're going to do x cubed, but a negative in front. Times that determinant. So I get 24x cubed minus 8x cubed. And then lastly, x to the fourth times 12x squared minus 6x squared. Oh, thank you, hon. So I do that math, right? Distribute, combine, and I get 2x to the sixth. Okay. And again, we're assuming that x is not 0. Kind of silly. All right, so that's just practice getting Wronskian of a 3x3. No, I won't ask you to do by hand anything higher than a 3x3. I don't even think I remember how to do a 4x4, anything higher than that. How about this question? Still gonna be depending here on Wronski. Determine whether the set of solutions, 1, 2, 3, is linearly independent. That's the same question, right, as asking you to do the Wronskian. Forgot that I typed that. Just a different way of asking you the same question. So you might want to pause the video and go ahead and do this, right? I'm putting y1, y2, and y3 in here and doing the derivatives on down. Doing 1 times negative sine 2x times positive cosine 2x times. Now, I really love when I have zeros in my determinant work, because notice what happens here. When I'm doing the first one, sure, that's a little yucky. Minus a positive, so it's still minus. Of course, I got some Pythagorean things happening there, right? But notice what happens here when I do sine 2x. I'm going to be multiplying 0 times who cares minus 0 times who cares. Hello. And how about when I do this one? 0 times who cares minus 0 times who cares. Hello. So that was awesome. So my Wronskian is factor that negative 8 out. And what do you have? Come on in, right? Hello, Pythagoras. Therefore, yes. They are linearly independent. Woohoo! Verify that these given functions are solutions to the differential equation. We've done this before too, just not with as many. So a nice way to do this is to take a chart and organize yourself, put all your solutions here, right? This would be solution y1, y2, y3, y4. Notice this is a fourth order derivative. So I need derivatives down to the fourth. parentheses around that differentiates this from, people get tired of doing Roman numerals, right? Or dashes, right? Sometimes they'll go to Roman, sometimes they'll go to Arabic here, but if they do Arabic, they'll put parentheses to differentiate that from y to the fourth thing. So when I do my first derivatives, love that situation. Check this one. What do I have to do? I have to, you're plugging back into the derivative. So I need to take my fourth derivative and add it to my second derivative and see if I get 0. Do you? Yep. 0 plus 0 checks out. How about this one? Also love, the derivative of t is just 1, and then love. How about y double prime plus fourth derivative? Also 0 plus 0 checks out. Cosine, not too bad, right? Negative sine, negative cosine, sine, whoops, positive sine, and positive cosine. And I'm looking at the fourth derivative, which is cosine t, adding it to the second derivative, which is negative cosine t, checks out. How about this last one? Taking the fourth derivative and adding it to the second derivative, checks out. So yes, all of them, all of these solutions are satisfy the given differential equation. Last one. Oh, hi, Abel. You remember Abel's use of to find the Wronskian? What did he find out? Do you remember that? He said, "Hi, the Wronskian is this constant e to the negative integral of pt." But what was this? That was the coefficient on. Now, when we were doing just second order p of t was in front of y single prime if the coefficient in front of double prime was what? 1. So how are we going to expand that here? We have a third order. So what do you think p of t is going to be? It's going to be the function in front of y double prime if, I made this red for a reason. We're going to divide everybody by x, right? And now we're going to identify p of x along with its sign. And we're going to say that the Wronskian, well, Abel's going to say, the Wronskian is c times e to the negative integral of positive 2 over x. Woot woot. Okay? So just short and sweet intro to generalizing some of the stuff that we've learned before to higher order. All right? We will do some more of this in our next live session.